Pluto from the beginning. It's like it's not valid. Pluto's orbit transits another planet. That's not typical behavior for a planet. Pluto, a member of the solar system's planetary family, now stands as a remote and mysterious dwarf planet. Recent discoveries by astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the limelight, suggesting a surprising possibility. It may be on a collision course with Neptune. How can such a situation occur, and what are the consequences? Are we seeing a rare event, or is there more to this upcoming match? Let's look at the results of the Pluto-Neptune clash. Pluto's journey around the Sun is unlike any other planet. The orbit is very irregular, taking 248 years to complete, and the orbit is very different from the circular orbits of the main planets. In addition to this remarkable feat, Pluto's orbit is tilted 17 degrees to the plane of the ecliptic, making its orbit very different from other orbits in the solar system. Despite its unusual orbit, Pluto crosses Neptune's path every 20 years. This proximity begs the question, why was there no collision? The answer lies in the characteristics of other celestial bodies. Studying Pluto's orbit has puzzled astronomers since its discovery. Unlike the orbits of other planets, Pluto's orbit presents some problems because it crosses Neptune's orbit. The stability of Pluto's orbit in the midst of these difficulties shows the complexity of the celestial mechanics, especially the three-body problem of Pluto, Neptune, and the Sun. Astronomers have identified the main factors that keep Pluto in orbit. A close approach would cause Pluto to cross Neptune's orbit, keeping it spaced apart, reducing the chance of a collision. Additionally, the latitude and VZK oscillations contribute to Pluto's orbital stability by preventing it from drifting too far towards Neptune or out of orbit. Despite these conservative measures, annual simulations have shown that Pluto's orbit is highly technical, with small changes in initial conditions causing large differences over millions of years. Understanding the dynamics of Pluto's orbit will not only shed light on the interactions between celestial bodies, but also increase our understanding of the solar system and distant worlds. By continuing to study and observe, we will discover the mysteries of the universe, the mysteries of celestial mechanics, and the dynamics of our ever-changing universe. However, Pluto's unique orbital characteristics have shown great stability over large periods of time, minimizing turbulence. Recent computer simulations have deepened our understanding of how gas giants such as Neptune, Jupiter, and Saturn affect Pluto's orbit. Neptune has a special relationship with Pluto and exerts an influence that helps maintain Pluto's orbital stability. However, Neptune is not alone in this process. Jupiter's pull and Saturn's support are very helpful. These simulations show that Jupiter's influence alone can regulate Pluto's orbit over billions of years. Neptune, Jupiter, and Saturn seem to be working together to protect Pluto's orbit in space. These features are essential to maintain order and predictability in the world. Without these stabilizing mechanisms, the solar system would become more chaotic and unpredictable, potentially leading to collisions or disruptions in stable orbits, with ripple effects across the sky. Knowing Pluto's orbit is important amid discussions about a collision with Neptune. It is a great insight into the dynamic nature of our solar system. The case of Pluto shows how unstable orbits can be balanced through the complex interaction between spacecraft and orbit mechanics, and emphasizes the importance of observation and keep learning. Deep space exploration often confronts us with the unexpected nature of celestial bodies, as illustrated by the orbit of Pluto. The theory of orbital chaos, that the orbit of an object strongly depends on its initial conditions, explains Pluto. Even small changes in its position or speed can lead to large long-term changes in its trajectory. Predicting planetary events involving chaotic orbits like Pluto's is a major challenge due to its unpredictability. While annual projections provide insight, they also emphasize the limitations of our predictive abilities, relying on initial conditions and complex interactions. Moreover, Pluto's chaotic orbit serves as a reminder of the dynamic and evolving nature of the universe, highlighting the vast gaps in our understanding. Understanding the gravitational influences of giant planets on Pluto provides valuable insights into the broader dynamics of the solar system, emphasizing the far-reaching effects of each planet's presence and position. So why are prominent astrophysicists like Neil deGrasse Tyson only now raising concerns about a potential collision between Pluto and Neptune? Despite these complex forces at play, Tyson's perspective, rooted in expanding knowledge about our solar system, offers insightful commentary on the evolving understanding of celestial mechanics and humanity's enduring fascination with space's mysteries. Tyson views Pluto's reclassification not as a demotion but as a necessary adjustment, reflecting our evolving understanding of the solar system's composition. His approach to celestial mechanics emphasizes continuous learning and adaptation, and sees the complexity of orbits like Pluto as a reminder of the vast unexplored regions of the universe. Tyson believes that the illusion of these unknowns is what makes astronomy so exciting. In addition, Tyson understands the role that space events play in creating public interest in astronomy. He sees events like Pluto's reclassification as an opportunity to spark public imagination and curiosity about the universe, by discussing the dynamic and sometimes unpredictable nature of space engines. Tyson promotes a deeper understanding of the wonders and mysteries of the universe. Along with other scientists, Tyson is at the forefront of warning people about the dangers that Pluto's erratic orbit can cause. After years of studying Pluto, he raised concerns about a collision with Neptune and emphasized the huge consequences it would have on the planet, including Earth. If Pluto collides with Neptune, it would be rare and dangerous in our solar system. The collision would release so much energy that it could shatter Pluto and scatter debris throughout the solar system, possibly causing damage to other planets and their moons. The collision may affect Neptune's atmosphere and orbit, depending on the conditions of the collision. Michio Kaku, best known for his work on string theory, has a unique perspective on the controversy surrounding Pluto's orbit. He sees the study of Pluto as an important part of the future of space exploration and sees insights into planetary interactions and orbital dynamics as important to solar system navigation and planning. Missions to distant worlds. Kaku believes that understanding celestial mechanics will lead to an understanding of the fundamental laws of the universe, similar to his work in theoretical physics, particularly string theory. Kaku also agrees on the possible scientific significance of the Pluto-Neptune collision. This event could provide an observational approach related to string theory, which may shed light on forces and particles under extreme conditions. The waves produced by this collision could provide data to test string theory's predictions about gravity and space. In summary, Pluto's orbit illustrates the complex relationship between stability and chaos in the solar system, providing important insights into the mechanics of climate and climate. Original of the world. Influenced by the influence of nearby planets, especially Neptune, Pluto's orbit adds complexity and dynamism to space. However, the three-body problem is only one of the many mysteries of the universe waiting to be answered. Predictable accidents like planetary collisions, while rare, cannot be ignored. Planetary orbits are affected by many factors, including gravitational interactions, as discussed in the three-body problem. In systems like TRAPPIST-1, as well as many nearby planets, orbital interactions create orbital resonance, which can cause instability over time. However, the collision will not be imminent, and scientists will understand the dynamics of the universe in nearby systems. Rogue planets that are not associated with the stars introduce another element of surprise. Ejected from star systems by gravitational disturbances or celestial events, these travelers can travel great distances and cross paths with other star systems. While collisions are possible, the vastness of space reduces the likelihood significantly, with rogue planets being relatively rare. During galactic mergers, while direct planet-planet collisions are improbable due to interstellar distances, the immense gravitational forces involved can disrupt orbits, ejecting planets into intergalactic space or triggering collisions within their host systems. Such events may even lead to the formation of new celestial bodies or stars. In our solar system, theories suggest that the late heavy bombardment around 4 billion years ago resulted from gravitational disturbances caused by the migration of gas giants. This period of increased comet and asteroid collisions altered the trajectories of numerous bodies, impacting terrestrial planets like Earth and shaping their surfaces and geological histories. These examples show the profound influence of gravitational interactions on celestial bodies, shaping their orbits, composition, and ultimately the evolution of the universe. As stars grow and lose mass over long periods of time, the planet's orbits can expand, possibly leading to transitions. This phenomenon is particularly evident in systems where stars reach the end of their life cycle. When a star ages and changes mass, for example during a red giant phase or when material is ejected into a planetary nebula, the planet's equilibrium changes. This can cause the orbits of the surrounding planets to be pushed outwards, or even more strongly, especially in multi-star systems where gravitational interactions are observed. In such systems, the gravitational pull of multiple stars can lead to unstable orbits, increasing the risk of being absorbed by other stars, colliding with or being pushed into interstellar space. Although actual planetary collisions are considered unlikely due to the vastness of space and the small size of celestial bodies, these phenomena continue to interest astronomers and astrophysicists at a great insight into the dynamics of planetary systems and the evolution of galaxies. The study of Pluto's orbit represents the continuing quest for knowledge and understanding of space exploration. Through their contributions, Tyson and Kaku show how each discovery adds a new layer to our understanding of the universe and reinforces the interconnectedness of all celestial phenomena.